Parveen. Actually, what is the duration of my talk?
90 minutes, 90 minutes, up to 5 o'clock.
Okay. So maybe what I will do, actually, the participants can ask questions in between also. And if they don't ask, actually, in the last, maybe 15 minutes early, I will stop and then they can ask the questions.
Okay. So
whichever way.
Definitely. But I would like to introduce regarding the audience also. So we have 96 participants. Out of that, 35, 36 are the research scholars, students means MTech and PhD, and near about 60 are the faculty members across the country. So accordingly, you can plan and you can discuss.
Actually, I have given one similar thing in the NIT. But anyway, actually, basically, this is be useful.
So you can.
Okay. So good afternoon, everyone.
Sir, please little bit increase your volume little bit.
Okay.
Yeah.
Now it's okay.
Now it's okay.
Yeah, it's slow. So good afternoon, everyone. So basically, this talk is on DFIG for DC microgrid. So actually, if somebody can ask questions in between, I will love it, because at least I know I'm talking to somebody. So participants are highly encouraged to interrupt me and ask questions, because that's how I feel connected. And I like always offline kind of interaction, but now it's not possible. But please do ask questions. Thank you.
Okay.
So going forward, basically, all of you know that DC microgrid is becoming popular in power systems and power supply, basically. So you all may be knowing the reasons for that. So the DC microgrid, why it is important is like it is basically even independent of frequency. So that's why it is easier to transfer power from one place to another between let's say, and most of our loads are actually DC. So let's say so actually when we use any electronics or something at home or at the offices, we generally convert the AC to DC, right? So we do that thing because the supply available to us is either three-phase or single-phase AC at our homes and all that. And that is why most of the instruments were made according to that. But actually, frankly speaking, let's say the PC load or DC is always preferable in terms of loads also. And let's say in terms of sources nowadays, we all know that the solar PV generation is becoming more and more. It is entering in a higher percentage in the power systems as a renewable energy, and that is a DC source. So if you have to connect it to the AC grid, then you have to put an inverter and do that. So there, actually, if this is DC microgrid, it is always easy to connect to a solar PV kind of thing. And so EV also, we know that EV works on batteries, and so generally there will be a V2G and G2V operation going on for charging and even regeneration to the grid. But again, if the grid itself is DC, then this process becomes simpler. And actually, if you charge the EV from a DC microgrid, you can adopt a DC fast charger very easily. And one more thing is like this battery. So battery, we all know that is a DC source, and basically it can even take back the power. So it's also a DC. So most of the things are are DC kind of thing. So this is let's say if we talk about a small area in a city, or so it's always, DC is always preferable. So now it is becoming popular. Maybe a city or something like that. Now, how to integrate the wind generation into this? So that is a basically the question was always, because it's another popular source of energy. So this was, like the thing. So if so, maybe I'll go back and forth in my slides. So basically, if you talk about wind generators, so these are the two configurations. One is basically, let's say, induction generator. It can be a PM also. So this can be a PM SM machine also. So let me write it. Let me write it. So this can be a PM SM also, right? So if you just see, so nowadays PM also PM SG, what you call PMSG or SCIG. So if you talk about this kind of systems, in these systems, like you don't have, so you have only have stator windings, and in PMSM you have a permanent magnet on the rotor side, but in a skull cage it is a shorted rotor, right? If this is the thing, sorry. So the thing is like, actually the drawback is that the wind speed may not be constant, so it works at certain range, right? So you get MPPT at different values of wind speed. The wind speed, let's say, varies from 8 meter per second to 12 meter per second, and you get like there will be so at every speed there will be a different power, right? So you have to understand what is that, and that you have to generate. But because of that, let's say if you have a synchronous generator, so let's say the speed varies here, the speed of the voltage what is generated at the stator winding will the frequency of that is proportional to the speed of the rotor. So that's why, but we have to connect it to 50 Hz grid. But because of the speed change or variation of the wind turbine, so this the frequency of the voltage generated here and the frequency of the voltage, even the magnitudes, will not match. And how can you connect them? So the only thing what we can do is like to convert to the DC, and so once you convert to the DC, frequency independent, you can keep any frequency here because you're converting anyway to DC. You take the power, the AC power at variable frequency in terms of fixed voltage, 0 Hertz, so that is DC. Once you take the power, you are free to connect to any AC source by modulating the AC voltage generated here by suitability modulating this inverter switching signals. So in that way, what are the PWM voltages generated here will be of 50 Hertz, and the voltage is suitably leading so that power can go from here. So all of us know that. So filters are basically inductors. So power generally goes from leading voltage source to the lagging voltage source. So you have to generate a voltage which is leading this voltage, but at the same frequency, and there has to be synchronized. So this is the bottleneck of this system. Bottleneck means if you have a 1 megawatt induction generator, both the converters also have to be similar rated. So here, that's the kind of drawback. So for wind power, generally the second system is used. It's called DFIG. DFIG means double-fed induction generator. Double-fed induction generator is nothing but a slip ring induction generator, where you have stator windings both on the stator and rotor. In this topology, what they do is like the stator is directly connected to grid, and the rotor is connected again by a back-to-back converter to the grid. So what happens? Let's say, so as I told, the wind speed generally varies from 8 meter per second to 12 meter per second. So if it, so basically you can say that uh, if we design a converter of two, like, so we all know that the frequency and the power are related. So so generally in this case actually I can tell, yeah, so the power converters have to be designed for speed proportional to 12 meter per second, because so you will get, let's say, maybe let's say if we say that 12 megawatt for 12 meter per second uh, 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 wind speed, and let's say 8 megawatt for a 8 meter per second, right? So you have to design these converters for 12 megawatt, both those converters, because it can always take a lesser power, right? Uh, but what we are wasting is like, we only have to operate, we have to only take, 4 megawatt in general, because the speed variation is only from, like we are unnecessarily putting a very, high converters here. But, that is simplified in this TFIG. How it is done? It's like that, this binding, so this machine is rated for 10 megawatt. In this case, machine will be rated for 10 megawatt, and so if we have to generate 8 megawatt, what we will do, we will take we will take always 10 megawatt from here, and when it is working at 8 meter per second, we take 2 megawatt power back from here. So in that way, this 8 meter per second is actually generating 8 megawatt to the grid. When we are working at 12 meter per second, again we'll generate 10 megawatt from here and 2 megawatt from here. So we'll generate, power is going out from both sides. So they are adding up in basically at higher speeds than 10 meter per second. So 10 meter per second is our synchronous speed. So, the speed proportional to 10 meter per 10 millisecond of the wind speed is our. So what is done here actually? So done here is like, this is the slip power. So all of us know that rotor handles the slip power in a slippage induction machine. So we are and slip is only proportional to the 2 meter per second, right? So 10 plus 1 is 2. So if 10 minus 2 is 8, 10 plus 2 is 12. So the rating of this power converter is just 2 megawatt. And here there is no power converter. So can you see the difference? Here the power converters, two power converters, each has to be rated at 12 megawatt handling power. And here just we have changed the machine from, so here actually we need a 12 megawatt induction machine. We need 12 megawatt of each of these converters. In this, for again the same system, the machine is actually 10 megawatt only, not 12 megawatt. And secondly, the power converters are only 2 and 2. 2 megawatt here, 2 megawatt here. So can you see, the huge difference? Huge difference, and the cost of this system and this system is, at the maybe 1:2 ratio or something like that. Even more than that. So that's why, for wind kind of application where actually the wind speed is of limited speed variation, this kind of system is used. So this is the conventional DFIG system. Okay. So basically, 1 minute. So allow me to be, editing, so this is basically, so this is how I teach my classes also, I keep editing the things. So this is conventional DFIG system. And so this is conventional DFIG system, and this you can make out this conventional DFIG system is suitable for AC grids. See here, this system is connected to AC grid, right? AC 3-phase grid. Now, so this is the thing, right? So actually, when we talk about this requirement, we're talking about DC microgrid. And now, if you want to integrate this wind turbine to this thing, how to do that? One way is like to go for this kind of system where this DC can be connected to the this DC can be connected to the DC microgrid. So there's one possibility is there. But you know, all of us know. So even for that, no, you need 12 megawatt of induction generator and here 12 megawatt because the whole power has to go out from here. But can we use this system? So this system has DC only here, nowhere else. So how to connect this system to a DC microgrid? That is the now the research is going on from last few years, and so we are also working on that. So what actually I will actually this is a very general presentation, but it is good for academic purpose because students have to learn. So what we are working now is this kind of system. This kind of system. So in this system, again, you can make out this wind power. You have a 10 megawatt, let's say slip induction machine. You put a diode rectifier on the stator side. So again, it was connected to grid, AC grid directly, but now you have to connect to a DC grid, right? So you put a diode rectifier. So okay. So nothing has changed much. Now, on the stator side, again, you are always generating 10 megawatt as in the previous case. So this speed is varying from 8 meter per second to 12 meter per second. Machine is rated for, let's say, 10 megawatt. So 10 megawatt is power is going from here. And what this will do, this is again rated for 2 megawatt, proportional to 2 meter per second. Okay, so when you are looking at 8 meter per second, it will, so 8 meter per second, actually you are, so here 10 megawatt of power will flow, but 2 megawatt of power will come back from here. So on the DC load and the this source, so they are always talking about 8 megawatt. So 8 megawatt is actually transferred to the load when you are working at speeds less than 10 meter per second. But when you are working at speeds above 10 meter per second, so you have to actually generate 12 megawatt. So 10 megawatt will come from the stator, and 2 megawatt will come from here, from the rotor side, again to the DC link. So the power is getting added in super synchronous mode. So you can the synchronous speed is proportional to 10 meter per second and 10 meter. So this is the what a slip-ring induction machine is capable of doing. So it allows very low. Can you imagine like only 2 megawatt of power from 2 megawatt power converter here, and in terms of SCIG or PMSG, you need a power converter of 12 megawatt for the same purpose. And so this is a highly optimized system. But where is the complexity now? So you get you don't get freebies. So so let's talk about that. So this presentation is a general presentation which I have made earlier. So I just want to tell the participants, who are new to this area, that how the slip-ring induction machine works. It's not conventional machine, right? It's not a skull cage induction machine. So skull cage induction machine we study even in our UG undergrads. We have some idea how to you have stator windings. You have a stator winding available to you, like for feeding stator voltages at certain frequency from an inverter or something like that. But how this doubly fed means slip-ring induction machine is operated. So my presentation is along that lines. So actually some work we have done for even standalone. So the loads can be anything, right? So either basically, let's say, so a any system is connected to DC grid, but who has formed the grid? Who has formed the grid means somebody has to form the grid also, right? Either you connect to a formed grid or you make your own grid. So there is a two different thing. It's a basically grid is formed by somebody. Let's say a battery has formed the grid, and this wind energy is just pumping the power to this grid. Another mode can be standalone mode, or where this is the wind generator itself will maintain the DC grid. This voltage will be maintained by not by battery but by this. So there are multiple ways you can see the system. So if the grid is available, the power generation is easier because you don't worry you have to just pump currents, DC currents to here. You don't have to worry about voltage, who will regulate it and all that. But in a standalone case, it becomes slightly complex because now the whatever voltage generated, you have to regulate it. So let's say if there is a higher load, you have to support. So load has to be supported by this. Maybe there will be help from other sources, but the job is more difficult. So voltage controller has to be in picture. But in a grid connected system, there will be no voltage controller, VDC controller, because somebody else will be doing that job. So let's go forward. Basically, so that's what I have told here, like standalone thing and all that. So that is not important. So what is slipping induction machine? So slipping induction machine, I just want to tell all of you may be knowing, like you have a stator windings and they have a rotor windings, right? So we all know that. So we are talking about generator now. So basically, what is generator? Generator means you are getting power out from the stator terminals. The power is negative here, right? So who is providing the power? The power will be provided by some prime mover. So it can be wind or it can be anything. So it will be actually rotating the rotor of the winding. And how you have two places, two windings to take out the power, stator and rotor. So and for the operation of the operation, what we are looking for, the frequency also has to be constant at the rated. So hello, can anybody respond? Are you able to hear me, right? I'm talking to my computer only.
Yeah. Yes,
Okay. So that's why, so this is AC and it can be rectified to a DC for a DC system, and that DC can be connected to this. If the DFIG system is what? You put a rectifier here, and that rectifier is connected to the. So what is DFIG system? So basically here you have a rectifier, and that is connected to this system. This is basically rectifier. Okay. So this system what we are talking about, right? So for this system, so here, no, like, so here you have a basically even DC loads connected, right? So DC grid or DC load. So basically, okay, so this is connected to some basically DC loads. So this system, now, so what is the thing is like you don't have any grid here, okay. So you have to maintain rated voltage here. So in this kind of DC, the grid is not available, right? You have to maintain this US, the stator voltage and rated value, and the stator frequency also 50 hertz. So you have to maintain that, right? So nobody else is maintaining. You have to maintain, right? So, and prime mover will be run at any speed. So prime mover can run, let's say, from 8 meter per second to 12 meter per second, right? But you have to maintain this frequency proportional to 10 meter per second. So this plus minus 2 will come from here, omega r. Omega r can vary from plus 2 meter per second to minus 2 per second, such that the difference of these two frequencies is always maintained as 10. So what is omega s? Omega is nothing but omega r plus omega m. So that if you have to maintain this as 10, if omega m or omega varies, omega r can vary suitably, such that omega s is always proportional to 10 meter per second. Okay, so in cases where omega r is positive, okay, it means that so if it's positive, then you are adding 10, right? 10 and 2. So in that case, no, if plus omega r is power is coming towards this machine. So what will actually happen? So in one case, power is so this is a bidirectional system. So in one case, when omega r is positive, power will come back here, and when omega r is negative, power will go back here. It will go from, so when it is 12 meter per second, so what happens, this will be 12, this will be 10, and this will be, minus 2. Minus 2 means power is coming out of this rotor side to the DC link. So 10 megawatt will come from here, 2 megawatt will come from here. When this omega is running at 12 meter per second. But when it is running at 8 meter per second, n will go from here, n will always go from here, but 2 will come back, so that actually the DC load is seeing 8 megawatt because the prime mover is 8 megawatt. So, this is the system. So how to, what to do? We are saying just vary omega r and all that. Is it so easy? Like, is it so easy, or like, do we have to, synchronize with the grid, understand what is the rotor speed? All these things, information has to come inside this, converter control. So that is the whole, we have to understand with respect to the control. So I want to tell you about that in this talk, what it is. So basically, as I said always, that omega s is the synchronous speed of this induction machine. This is an induction machine, right? Although you have rotor windings available and the terminals are also available, still an induction machine. So any speed which is above rated speed or synchronous speed is known as super synchronous operation, and anything below is called subsynchronous operation. So at 8 meter per second we are doing subsynchronous mode. About 10 meter per second we are doing super synchronous. So okay. So basically this was conventional DFID system. As I already told you, this is conventional standalone system DFIG with, but with still with the AC grid. So here no grid is there, but you are generating a three-phase AC system here. But now what we have done, we are putting a diode rectifier here and connecting the DC to here. So basically, the system has become slightly different. Okay. So these are conventional DFIG. So here the whole job is how to operate this converter. Even the DFI system, how to. So for that, we have to understand the full modeling of slip in induction machine, where the stator is connected to grid. So this is the only controllable power supply you have. So VR and omega R is the only control voltage at any frequency, at this frequency. This is already there. Machine is already there. The prime mover is already there. So all these things have to be modeled. And that modeling will help you to design the control system for this rotor side converter. This actually already I mentioned. The power, so depending on whether slip is positive or negative, the power in the rotor side converter will either flow here or flow backwards. But this is always at rated value of the machine. Any questions? Actually, if somebody is putting any chat window, I cannot see because I am seeing my screen, right? If anybody is asking any questions, actually you can speak up. I cannot see chat window.
Nothing in chat box. Nothing.
Okay. So I hope somebody is listening also.
Hey, everybody is listening. I think given the 15 minutes in last, I think they will ask at that time.
Achha, which time? During the last time. Okay. Okay. Actually, you can ask in between also because otherwise, I am okay with that.
Okay.
Actually, I like it because it's. Okay, so this is the system. So actually, if you want to plot this with respect to speed, you can even plot it. So this is basically grid connected system. So actually, basically earlier, actually I had worked on grid connected systems and standalone systems for AC thing. So for AC kind of topology, I've already had some kind of experience earlier, and also for a standalone AC DFIG, right? So that whole experience was very useful to work on a DFIG DC system because the machine has not changed, the operating modes have not changed. Only you have to take care of now different things, like you have to take care of the DC voltage rather than AC voltage, which is simpler actually, I feel. And you have only one converter. Earlier you used to have two AC converters, right? So this converter was supposed to. So this converter is working at variable voltage, variable frequency, omega R and VR. And the job of this converter was to maintain DC link voltage. And so this is a bidirectional converter. This was also bidirectional. So this is kind of front-end converter, what to say. So this converter, the job of this converter is to maintain the constant DC link voltage and allow bidirectional power flow here. So when the power comes out of the rotor, you allow it to go to grid, or when it needs power to the rotor circuit, to take it from the grid and give it. So such that you maintain the DC link voltage constant, and also the currents here should be sinusoidal, right? So this the job. So both are working on vector control. So this is working on vector control of machine. This is working on vector control of the grid. So this is grid side inverter. So it was quite complex, but now we have to work only with this kind of thing. So it is very simpler. So how to work in this kind of system? So this is our system, right? Even though it's a AC here, so there is no issue, right? So So this is our new system, right? So this is so on the stator side, always the power is going to the DC link. On the rotor, it is bidirectional. So how to work with this system? So you have to sense all the currents to understand. You have to even sense the stator voltage, because you have to maintain a rated value and rated frequency. In this case also, you have to sense stator currents, three-phase currents, the rotor currents, and in this case the DC link voltage, because you have to regulate the DC link voltage. It is a standalone case. So all this, a lot of sensing will be required. So generally two in a three-phase system is a balanced system. Only two quadrants are enough. So two here, two here, two here. So 6. Then this 7, and this 7 AC variables. Then basically, if you want to sense even the DC link voltage, what is going in load, then 8. Then if you want to you want to understand the position of the, and that is you will require, if you're not doing sensorless operation, the position of the rotor surface. So one encoder will be required, and this. So it will happen. It will become 9. In a case of AC system, it was exactly 12. I remember. So 12 signals has to come to the DSP controller or whatever controller you're using. So and then with all the information in hand, you can take decisions suitably. The decisions will come out in terms of the switching pulses, switching gate pulses to this inverter. So how we go about it? So first we have to understand, the slip induction machine. So in a squirrel cage machine, we always know that this rotor side is shorted, right? You have a cage on the rotor, and then it's shorted. So it is 0 here, and only this the voltage is to be controlled. But it is not true here. In this case, basically this is a kind of fixed voltage, fixed frequency. It is not variable, and this is what is variable. So use non-zero voltage, right? And this voltage and frequencies will be controlled through an inverter. So this is totally different system compared to a squirrel cage. So if that is the case, you have to understand not only the rotor circuit and the stator circuit, you have to see how the stator currents and rotor currents together forms the torque. So torque is basically a function of cross product of stator current and rotor current, which has to be understood. And when you do the vector control, some of you maybe used know the vector control of induction machine or squirrel cage induction machine. So what we do there, we have to catch hold of one of the fluxes and go and sit there, actually make that as a reference plate. So in a case of conventional, if you say squirrel cage induction machines, FOC, vector control, we use rotor flux as the flux for doing the DQ coordinates. But in this system, since the stator voltage and stator frequency is almost fixed, so once that is fixed, stator flux is also fixed. So that is why you choose always stator flux as the reference axis for this kind of slip induction machine setup, because stator voltage and frequency is constant. So the stator flux is chosen as for maintaining D and Q. So this will be your D axis, and perpendicular will be your Q axis. And sitting on this DQ, you have to control the rotor currents now. Because the rotor converter is only controllable, right? Stator, there is no converter. So you have to control the rotor currents in this DQ, and so what you will inject the rotor currents in DQ fashion, it has to be at slip frequency omega r, and the omega r is is related to omega m plus omega s. Omega s minus omega m. So I think somewhere we have seen that omega r is omega r is equal to omega s minus omega m. Omega s is 50 hertz, and if omega m varies, so that omega r also has to vary. So omega m, if omega s is supposed to do 10 meter per second, and omega m is varying from 8 to 12, the omega R will vary from plus minus 2 hertz, plus minus 2 meter per second. So that is a varying frequency. So the frequency of this rotor current has to be that omega R. So basically, those who know some basics of FOC can appreciate this, and others will actually can get a glance of this so that they can read it later. But I'm just introducing you. It cannot be, you cannot start this topic as a new and complete it in the same thing. Actually, basically a student participant should have some kind of background on that. Somebody who has taken a drive course can understand. So this is the rotor currents. So this basically now in this actually I told you. So here omega the Vs is stator voltage. So this is a constant, right? Vs and omega s is constant. So this is more like a constant equation. But this is Vr is the variable term here. Vr and Ir. So these equations we have to understand. We have to transform this equation to dq coordinates. And what is the dq? Coordinates is stator flux, which is Vs by omega s. That is Is. So this is 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 nothing but Vs by omega s. So once we basically this is the stator equation in terms of dq. This is the rotor equation in terms of dq. This is more or less a constant equation, but this is a kind of controllable equations, and we understand all these things together to get a better understanding of the plant. So in terms of control systems, our plant is the machine, right? So until we understand the plant very well, we cannot design the controller. So this is the whole modeling is to understand the plant. So let us say we understood the plant, and that will help us to sorry, some sounds are coming. 1 minute. I think this WhatsApp is creating problem. Okay. Now our whole world is PC. Okay. So actually in this so we have to write we have to structure our control blocks in DQ frame, right? So so all this IRD, IR2 are rotor currents in DQ frame, and this all feed forward terms and all that are we know from the modeling equations. And you put PI controller on D axis current and Q axis current. So what is the D axis current do? We all know that D axis is nothing but the flux axis. So D axis is a flux axis. So the job of this D axis current controller is to maintain this flux from the rotor side if you want to. Otherwise, it is available from the stator side. And the job of this IRQ is the active power. So what power you're generating, that PR, the power coming from the rotor. So this will decide how much power has to be generated. So this is a generation reference. Basically, you can say the torque reference in this case. So this is flux loop. This is the torque loop. And basically, you can implement as well as it's possible in this machine. Because you have a lot of information available, stator current, rotor current, stator voltage. So it's always possible to do some kind of estimation of okay. So this is such as algorithm. So these are some of the experiment results. What we have done for AC system. So you can see that these are perfectly coupled system D and Q. Basically, this is out of phase. So it is generated on the road. So if stator currents and stator voltages are out of phase, it means power is going out. So I told that it's possible to generate flux both from the stator and rotor. So in this case, the whole flux is given from the rotor. So that's why it is perfectly UPF on the stator side. But let's say if you don't do that, then stator also has to supply the part of the flux from the stator side. In DFIG DC, you can't do any DFIG DC. There is no AC source on the. Sorry, there is no source to supply flux from the stator side because stator is connected to that rectifier. So that's why the full flux has to come from the rotor side only, and this will be the case. So the power factor at the stator will normally be UPF. So this is an interesting waveform where actually you can see that the speed is varying from let's say it's varying from let's say 9 meter per second to 10 to 11. So this variation is basically, you can say that you're varying from 12 meter per second to 10 to let's say 11 to 9. So what will happen? The rotor frequency will change the pace. Because in one case the power is coming in the rotor circuit. If you see, if at 9 meter per second power is going to the rotor, but in this when you are working at 11, the power is going out of the rotor. So phase sequence changes in the rotor side. On stator it will not change because stator is always out only because it's a generator. So this but this is not relevant in terms of DFIG DC, but this is a front-end converter control, what we generally do. So this is a FOSI of that. Anyway, I will leave it. So actually, my second, so one of the work was grid connected DFIG AC system, then grid stand-alone DFIG system AC system for AC network. So this was another work we have done. But in this case, as I told, there is no AC grid available to us. So if AC grid is not available to us, then we have to, we have to even generate a AC grid. We have to regulate it. Even we have to regulate the frequency. So we have to, basically create a three-phase AC, and we have to maintain not only the magnitude but the frequency. So that is very challenging. So in this case, a lot of so this was one of my MS work, what I've done in masters. So and another interesting thing is like let's say if there is a non-linear load connected to the grid what we have formed, then who will take care of the grid quality, power quality? We only have to take, because we are the source. So that is a very interesting thing. How we deal here. Actually, let's say you have a nice linear load, but let's say you have a non-linear load also connected in the same thing, right? So if this is a topology of the AC DFIG AC, you can say. So the interesting thing is like you have a grid side converter which is connected to shunt of this grid what you have formed on the stator. So this grid you have formed on the stator, and this is connected to take care of the rotor side power flow back and forth in sub-single, super-single operation. But incidentally, this is also connected in shunt to this grid, and that's why this grid side converter can also act as a. So here it is just a bidirectional power converter, but it can also support active filtering. So it is if it's connected in shunt, it can act as a shunt active filter. So so this additional job of supplying non-linear current to the non-linear load can be done from this converter, and that is very interesting thing what we have done. So there's a lot of challenges for external operation because we have to do everything, and so that is how we do. So, so in a standalone case, basically there is no source for providing reactive power to the machine for, you have to give reactive power for generating the flux. So if it's a standalone case, there is no grid who will support. So you can use a battery bank in this DC link and do that. But a novel feature is coming here. Actually, since your primer is running, system is already in motion. So you can use a basically a small DC generator or something with PM DC kind of thing, where you can generate a small. So system is running from prime mover. This can generate a small DC voltage, say in the armature, and that you can use for initially so providing the initial flux. But after that, this can work on its own. So this was, so you can see for compared to the what we have done there. Here, no, you have to have a AC. I'm talking about DFI standalone DFIG AC system. So we have to maintain the the three-phase voltage, right? Three-phase voltage at certain frequency. So the magnitude of the voltage will be maintained by maintaining the flux. So this additional controller has come into picture, and the frequency you have to also put a controller. So you have to put a voltage magnitude controller, three-phase. The frequency of that you have to maintain separately. So this additional two jobs you have to do with all the regular things what to do for it. These are the results for a DFIG AC system. So you are able to. So we are able to generate. We are able to maintain the grid. This the performance of the grid side. So the grid voltage magnitude controller. This is the frequency controller. Both if they are maintained, you are able to maintain the grid. Then you have a current controller on T and Q axis of rotor winding. They are able to track. Then the sensorless operation is also possible here. And how the system performs to load addition and removal is also there. So this variation is what I was telling. When you move around synchronous speed. So if you go subsynchronous, super synchronous, or super. So this kind of variation you can see. So this was my master's work. This is what I was telling. Interestingly, if you have nonlinear load, you can compensate a large amount of that. So this is the uncompensated stator current, and this is the compensated stator current with the help. So here the FEC current is not doing anything. It is allowing the load to be. Load will be like this only. Load you can't help it. Only thing is like, can you allow this stator current to go bad? Because if stator currents go bad, the stator voltage also will be affected, which is a grid. So rather you make this uncertain as much as possible. You can allow this to, because this is a shunt rectifier. This is not the current which is actually maintaining the grid. So this is the current which is maintaining the grid. So we are able to do a bit of correction here, and so it was working to some extent. So the bandwidth of the current controllers were not very high, and we had to make, so this DXS was behaving much better compared to Q. It was able to do quite a large amount of compensation. This was the experiment setup of actually RC Bangalore electrical department. Actually, we have made a product also out of this. This product is also available. Anyway, now actually I will come to the basically I was talking all that time about DFIG system. So this work what we have done in the last few years in IIT Delhi is we worked on this system. So this was basically is in the family of that DFIG system. So since we have all the knowledge of those things done, so we have utilized that information, that understanding of the system, and we have created the solutions for this DFIG DC systems in the simpler system. Again, the philosophy will remain same, only the control loops will become different. So For this system, we don't have to maintain the AC voltage. We have to maintain the DC voltage of this, the DC standalone DC voltage. So we have to not only maintain the DC voltage, we have to regulate it also. So we have put a actual DC voltage controller. There will be no frequency controller because frequency is DC anyway. So this is very much similar to what work we have done earlier, but we have adapted it to the present requirement. So again, this is the results what we have done at IIT Delhi. So we again that the waveforms of which have, these are experiment results. So we are able to create a grid. So this is grid creation starting, and then maintaining it for load variations. And also this is AC. So again, as I said, so in the DFID system also, you will have subsynchronous mode, supersynchronous mode. So this with the speed variation from 9 to 11 or something. So the phase sequence of the rotor voltages will vary, right? One subsynchronous power will go inside the rotor and supersynchronous power will come out of the rotor. So this is a classical way of representing the speed reversal. But there are some disadvantage because since you're putting a diode rectifier on the stator side, the currents here will not be very good. And because of that, there will be some torque oscillations on the actual rotor. So that's the drawback of the system. Although it is very simple, but this drawback is there. This is the stator currents. This is the stator currents, stator voltage. It will not be sinusoidal because the diode rectifier is sitting there. Then we have improvised the system because what happened. So the conventional slip induction machine available to us is not 1:1 ratio. It will be always 1:3 ratio or something. A typical slip induction machine. So let's say you have higher voltage. If there's a 1 per unit voltage here, it will be 0.3. So how to bridge this gap? So we step down this thing, and the DC link will be pushed. This will be a lower voltage, but this whatever step down is there within the machine is a 1:n machine, right? So that 1:1 ratio we have compensated using a transformer, and so if you do that, you slightly you have to take care of that in the modeling, and that also we have done. And we have done the analysis of what kind of harmonic currents will flow in the stator. So those analysis is done. Basically, it will be 6th and 12th harmonic. So this, if you understand it, we can do something. This control block diagram and again the results. So here the control also is slightly different, but it's okay. So earlier, we used to do the VDC control from the D-axis thing, but in this system we have done it from the Q-axis, and that is interesting. That gives some kind of advantages compared to the previous system. And so basically, I can find okay. So it's our. So actually, I have completed my presentation. But actually, anybody can ask some questions. So basically, I think let's talk more than I will only talk. Anybody is free to talk. So most of our students actually, as I was told. So anybody who is working on DFIG or some kind of induction machine control or something. Participants?
Please. Participants, you can ask now.
It's full blank. So many students are there.
Yeah. 15 are there.
Why people are not asking questions?
Anyone?
I mean, this is not nice, not good audience. So let us interact, right? What is that? I hope maybe I can. If you think I can't answer any question, then it's okay. Otherwise, just talk. No, like what is that? So I think a lot of people may be working on power electronics or something.
Yeah.
Then they should be having some questions. Right?
Participant, please, you can ask. If you have any queries or questions, you can ask. Somebody asks, what were voltage, current, and power rating considered while simulation? Rating.
No, actually, so I have not I have only done experiments. So these are all experiment results. So experiment results for a 5 kilowatt system.
अच्छा 5 kilowatt.
So but actually simulation तो कर सकते हो megawatts में, but so it's all experiment results.
Okay.
But typical DFIGs actually, as you're correct, that typical DFIGs are in megawatts.
Megawatt, okay.
So these are experiment results in the lab.
Anyone here? Somebody asked.
May I ask?
Yeah.
One question to our respected person.
Actually, your
question is very much, I think. Yes. My question is that.
Your voice is slightly. I will stop.
You can write in chat box so I can read. Your voice is not clear. There is a echo. So you can write on the chat box. So, sir, there is one question from Satish Kumar Ramoji. Sir, is it possible to simulate in Opal RT hardware setup? Yes, sir. Dr. Amit.
Hello.
Okay, sorry. I was muted. So actually, in most of the industries, the simulation is actually done in OpenRT. So it's a hardware simulation, right?
Okay. So somebody asked.
So it can be done. So I have seen people doing that.
Okay.
One question I want to know. What is the percentage of efficiency in a DP? Maximum efficiency we can use.
Efficiency of what?
Efficiency of DFIG. Maximum. How much?
So efficiency of the machine will be 85 only. 85%.
85%.
So because that's a good point. Let's say when you go for permanent magnet machines, the efficiency will be around 95. But induction machine, all of you know that it has more losses compared to PM machine, and so that's why efficiency of DFIG is less only.
Dr. Susid Dikshit is asking if experimental setup is not possible, can we simulate it in MATLAB?
Why the MATLAB? Everything is possible. So actually, MATLAB is a good thing. Actually, what happens now? So initially, let's say you cannot operate this kind of big systems on hardware, right? It's a big system. Actually, I feel that. So because there are a lot of controls are running. So actually, we do this kind of modeling. So we make so these equations are available to us. So once we have the equations, you can always model in MATLAB, and that's how we also do. Like so, we don't bypass that simulation step. So initially we do simulations in MATLAB, only Simlink, and we make our own models. That also I want to tell you. We don't use any power system block set. We use, but beginners can use those things. But if you make your own model, you have more control over many things.
There is a one more question. Opal RT hardware setup like in OP4510 model.
Actually, that I'm not aware. Sorry.
Acha.
So I'm actually Opalati. Actually, I've seen my colleagues using it, but myself have not used it, so I can't.
And then I think it would be better they may ask to Opal RT people. They may ask.
They can help you. They can help you. So basically, even in General Electric, actually where I was there, so my colleagues were using Opal RT. So from the people who are from power systems, so those who are from power systems, they want to do these things. They don't go too much inside, the power electronics and all that, right? So well, they are more interested in the system studies.
Yeah.
They are not in the power electronics. So see, I am a power electronics and drives person, so I am more interested in how the switching is happening, how the current control is happening, all those things. But for a power system kind of people, where it's a wind farm, or you are connecting two DFIGs to two grids or something. So they don't worry about how the individual DFIG is working.
Yeah.
So they are more key as two wind generators are coming into a grid at different wind speed and how power system will behave.
Yeah.
So for that, Opal RT is a good option.
There is one more question. Dr. Shobhadi Bhattacharya. He is from this NIT Agartala and HOD of Electrical. He is asking which DFIG is implementable with offshore wind farm?
So why not? Offshore and onshore is how it makes a difference. So the kind of maintenance and that the DC generator will be sitting on top of the wave and top of the windmill, right? So DC machine is over now. The age of DC machines are over because it needs brushes on the armature winding, and that that requires maintenance, and it has all kind of problems. So the age of DC machine and DC generators are over because now we are. So that was there because we didn't have the capability of working with AC machines, right? Why we are not able to work? Because we don't have sophisticated power electronics or sophisticated DSP controllers. Now all these things are available to us, and so we will like to have our machines, which are maintenance free.
Dr. Nagin, would you like to ask anything? Any question?
Actually, we have a lot of PhD students who have done MTech from NIT Agartala. So NIT Agartala, actually, what I understand is, the power system and power electronics group is really good at the PG level now, because we had the students. Now, I think I know four MTech people who are doing PhD here.
Yeah. Recently, one Arjita is also joined after.
I don't know. Purva Verma is there. Shivashish Nayak is there. Shankara Rotala is there. Then Sumit Singh is there.
Is working with you also, no?
With me, Purva Verma is working.
Okay.
I think I don't know who was the supervisor for MTech, but with good work. Like the students are really good. So I want to tell at this forum that NIT Agartala is really doing very good in especially power electronics and So actually it's nice. So even coming and interacting with all of you in this. Actually we don't meet. We don't know each other.
Yeah. Recently, one of my students, that Arjita, directly after BTech, he joined the MTech there, and recently converted to PhD after that. that CGPA based. It converted to
Okay.
CGPA.
Maybe power system I may not be aware of that. So okay.
So, any more questions? Anyone? Please feel free to go and talk. So I hope. Okay. Someone is. Dear participants, if you have any query, you may ask. Otherwise, this is the time to say bye. I think now no more queries there, Dr. Jain. So, can we bind up here, or still you want to?
No, no. I think somebody is.
Khalik,
Mr. Khalik.
Sir, my question is that while we are integrated the DC and AC, whatever the generator we are connected to it, when it comes to the reliability assessment of the all the system, so how we can get assess the reliability of all the system?
Means like reliability in terms of.
In terms of
See, reliability is.
Reliability in terms of the availability of the energy resources in terms of the consumer side, not in terms of the utility sides. So how we can assess this with this microgrid?
Actually, I don't know. This is not my area. Like I'm clueless.
All right, sir.
I'm sorry, because reliability. See, you are talking about customers and all that. I think you work on that. I think from the power system side, that optimal load flow and load dispatch and all that.
Actually, sir, I am a PhD research scholar and currently working for the reliability assessment of distributed generation. So that's why I'm asking.
Yeah, that's actually. I'm sorry, Arrow. That is, I think that's a subject of restructured power systems, and I think actually some of our faculty works like Professor Abhijit Abankar and all this. Those are works on those areas.
His question is that there should be balance between the load and supply. The battery storage is there in DC microgrid for emergency period.
All right.
For enhance the reliability, batteries are also there.
All right.
That would work.
Acha, in those terms you are asking, okay. Yeah, so basically, so even though, let's say in any microgrid, I'm saying, let's say in any micro thing, there will be something, which is, we are very clear that it is there. Means they will be kept, as I said that, as Professor Arvind said that, typically, batteries are kept, or even DG sets are kept, diesel-based DG sets are kept, for the worst case. Let's say if everything other, let's say wind has gone, solar has gone, everything is, no EV is connected, and let's say something happens. So those, actually you have to, it depends on, how you, what you promise to your customers. So if you promise that, 24 will be available, 24-hour supply will be available, then you have to take that contingency into account that nothing may come and you have to still give power to them. So that backup you have to have.
In that case, optimum scheduling of resources are required to manage the reliability and the proper transaction. The power flow.
All right, sir. Thank you.
Then cost and other things will also come in picture, the setup and entire thing. So lots of things are there. But you can manage with that. As sir told, so even you can go for the generator also. But cost, again, the cost analysis is also required. It is also in one end. Right.
All right. Thank you very much. Thank you.
Hi, thank you.
Anyone else? Please. Okay, sir, I think Now no more questions. So can we stop here, or you want to say something?
No, somebody else is asking. Yeah.
Who is asking?
I don't know. Some sound has come.
Sound is coming. That is from your system or some other place.
Okay, I think if nobody.
Yeah. So now you can turn on your that camera also. That would be better. Yeah. Okay. Right. So very, I can say very technically impactful lecture, and I hope everybody enjoyed it. And definitely it will give the new thinking, new direction for in this field, and our participants will be benefited out of this. And from the NIT side, I would like to pay my sincere thanks to you for accepting our invitation and sparing your valuable time. I hope after pandemic situation will be over, definitely we will meet physically also, and I will invite you to visit this institute. As technologically, IIT Delhi and NIT are is also well connected. We have the MOU for the student exchange and other things.
Yeah.
Yeah. So as a technical institution, we are already friends, and we will try to maintain that. So thank you very much from our side. Thank you.
No, so thank you from my side also, sir. Actually, it's good to connect with the crowd of NIT and even other participants from the country.
Yeah.
And so this is my first interaction from NIT Agartala. So
Yeah.
and so as we have many students, actually, I had I want to make some kind of bridges to NIT Agartala for some collaborative work and
Yeah, definitely.
something. Okay, so
We will extend the cooperation from both sides, and definitely we will remain in touch also. So once again, thank you very much, and let's stay healthy, stay safe.
yeah, same to all of you, all the participants.
Yeah.
Thank you. Thank you.
Okay.
Bye.
So thank you one and all once again. And now we have one day, and that is Friday. So there will be two sessions in the morning. First from the 10 to 11:30, and second from the 11:40 to near about 1 o'clock. So first session is the technical session, and the second session is the art of living session. So I request you all please join both the sessions with the full of strength. And after that, there will be one examination, because as per the ATAL FDP, one examination should be there, and each and every participant at least score 60%, not less than that. Then they will be qualified for that certificate and other things. So I hope now we will meet tomorrow at 9:50. So first session will be delivered by one of the professor from IIT Mandi, and second lecture will be delivered by professor from the IIT Kharagpur. He is art of living teacher. So he is also a professor of psychology and other things. So let's meet tomorrow. So test timing will be after lunch. I will mention. So there will be a small valedictory and 20 or 25 minute test. That I will write on the WhatsApp. I will send the WhatsApp message.